Let me start with optimizing IP for IoT. Here we will be going to see that an IP, that is the Internet Protocol, is the key for a successful Internet of Things. So here it is going to be have the different types of networks. One is the constrained nodes and constrained networks, and optimization at various layers and on multiple protocols of the IP architecture. Here we will be going to see one of the architecture, that is adaptation layer for IP and IoT. So here it is going to have, there are 4 layers. One is transport layer, network layer, data link layer and physical layer. In between data link layer and the network layer, we will be going to have the adaptation layer. So from the physical layer, if you consider, so it is basically wired or wireless type of network that we will be going to have, and in the data link layer we will be going to have, we are going to use, we can say, some of the protocols like 802.14.4G and 4E. In detail, these things will be going to study in the next slides. Next, in the upper layer, we can say that in the network and transport layers, in the network we will be going to have IPv6 and, or we can say IPv4. And finally, in the transport layer, we will be going to have another 2 protocols. One is TCP and another is UDP. Basically, TCP is used for handshaking signals where the data is getting, you can say that it is reached, and in the case of UDP, we cannot assure that it is being reached. So the following optimization techniques are there for an IP. Already it is going to be available. So first one is that is a 6 low power WPAN. It is wireless personal area network to 6 low power. In this header compression is there, fragmentation is there, mesh addressing is there, mesh under versus mesh over routing is there, 6 low power working groups. And there is another protocol, we can say that the 6 TISCH and another one RPL. The functions of that is objective of the function, rank, RPL header, matrix. Finally, the authentication and encryption of constrained nodes. We will be going to have another 2 authentication and encryption tools. There is ACE and DICE. Let us start with the first one. That is 6 low power PAN to 6 low power. So here in the IP architecture, the transport of IP packets over any given layer, that is a physical layer, it is going to be usually, and MAC sublayer protocol must be defined. The initial focus will be on 6 low power PAN, WPAN working group, which has optimized the transmission of IPv6 packets over constrained networks such as IEEE 802.15.4, which is a IoT network. You can see here the proper distinguish between IPv4, that is IP protocol stack, as well as 6 low power and adaptation pack, that is IP versus IoT protocols. In IP we will be going to have the 5-layer network. It is physical layer, data link layer, network layer, transport layer and application layer. The physical layer in IP protocol stack, we have Ethernet physical layer and Ethernet MAC layer. Then these are all works under physical and data link layers. The network layer, we will be going to have an IP, Internet Protocol, and in the transport we have TCP is there, UDP is there, and ICMP is there. Then finally in the application we have TCP, HTTP as well as RTP. Similarly, when we come to this IOT protocol stack, that is the 6 low power PAN adaptation layer. There are so many n number of application protocols are there. We have here UDP and the transport UDP and ICMP. Network layer IPv6 is there. Then data link layers we want to have 802.15.4 MAC and as well as physical layers are there. So let us see that what is this 6 low power PAN. That is a header stack. So we will be going to have here, you see that the working group, that is 6 low power wireless personal area network group publishes several requests for comments for the idea, but RFC defines frame headers for the capabilities of header compression, fragmentation and mesh addressing. Now you can see here 802.15.4 header. First is IPv6 header compression is there, IPv6 payload is there. Next is fragmentation header. There is a fragmentation header is there, IPv6 header compression. This is same, there is no change in that. Okay. IPv6 payload. Again the mesh addressing, we will be going to have third layer, that is mesh addressing header, fragment header, IPv6 header compression, IPv6 payload. So header compression, how it does. Okay. So let us see that here 802.15.4, that header is there. Total of we can see that 1 byte and 40 bytes, 8 byte, 53 bytes. Total is 127 bytes are there. Here 1 byte is consumed by 6 low power and header if it is present. Then we are having IPv6 40 bytes, 8 bytes of UDP and 53 bytes of payload. So this count is a number of counts, number of payloads, so we can say a number of packets that it is going to count. Here this is for IPv6 and UDP header it is. Here in this case upper part is IPv6 and lower part is UDP layer. It is 6 low power header. For compressed IPv6 header it is going to be 2 bytes it is taken, and UDP is there with 4 bytes payload. Now here basically when we talk about at the top of 6 low power frame, that is upper part, without any header compression enabled. So full 40 bytes of IPv6 header is going to be used and 8 bytes of UDP header is going to be visible. But in case of this low power, that is bottom state, that is increases by 2 bytes to accommodate the compressed IPv6 header, and UDP has been reduced in half, that is instead of 8, 4 bytes it is going to be taken. And in this upper part, the lower 6 low power PAN, that header, only a single byte in that case, but in the second one it will be 2 bytes. Uncompressed IPv6 and UDP header is only 53 bytes of data payload, but out of 127 bytes the frame size in the case of this, that is 802.15.4. So only 53 bytes that is going to payload is going to be used here. It's in the same case. So instead of when it is getting compressed, the header compression has been allowed the payload to more than a double, that is from 53 bytes to 108 bytes, which is obviously much more efficient. That's why you should go for a compressed mode of communication. Now, what is this fragmentation basically? If n number of bytes are going to be there, we should